So, welcome everybody to session number 6 of my lecture on statistical energy analysis and hybrid methods. So, there was a long summer break, which I really enjoyed, and coming from ocean waves, we now come to waves and fluids. Again, one remark for those of you who are familiar with classical acoustics theory, you can skip that session. The idea and the focus here is really to derive the equation, the wave equation, but especially as we are talking about SEA and statistical energy analysis in the context of energy intensity and what is the energy content of fluid waves. Good, so let's start. Acoustic wave motion is something that is described by the equations of aerodynamics. For this we need 3 equations, and they are linearized because in acoustics we talk about very small fluctuations of the acoustic waves, and they are much smaller than, for instance, in aerodynamics or fluid flow. We have the continuity equation, which is the conservation of mass. We have Newton's law, which is in fact the conservation of momentum, and we need a state law. This is kind of rule, or let's say description of a fluid that gives us the pressure-density relationship. The equation of state could be ideal gas law or whatever. We will use the so-called Euler description of fluid dynamics. That means we will consider a fixed control volume and not a control volume that is moving in space, and that's something which is important to know, because there's another option which is moving with the fluid flow, but this is something that we are not using in acoustics. The dimensional space is described by Cartesian coordinates x, y, z as usual, and the velocity in the fluid we denote by v and an index x, y, z for the fluid speed, flow speed. Good. Let's come to the single equations, or let's say conservation equations. You can see here the control volume, and if we do the balance, we have some flow entering this volume, and we have some flow leaving this volume. It's the amount of which is density multiplied by the velocity in x, and it's the same here, plus a gradient of the density and the velocity. Please keep in mind that this is multiplied, so it could be a change in density, but also in the velocity if we have a specific flow field. Plus any external density inflow. It could be a tiny loudspeaker, it could be some explosion, whatever. So it can also be a change of density in this fluid volume. Good. If we write this, we got this equation. The density change in time with respect to time is the gradient of this product of density and velocity, and this is equal to the external change in density that could come from many different sources. We do the same now for the momentum. This is what we call the Newton's law. Here we have some other quantities. We have, let's say, an external pressure acting on this volume. It could also be a force that is acting on the cube in total. And we have, let's say, a momentum flow. So just see that this is the squared velocity and no longer the linear velocity, but the procedure in general is the same. If we do so, considering all terms, we get the conservation of momentum, which is the density. We have the change in velocity. We have this funny term here in the middle, plus the gradient of pressure, which acts as a specific force, and some whatever created external forces that could be available, and that we will later use very later in some additional sessions when we talk about sources. Okay, finally the equation of state. That's the relationship, as mentioned, between pressure and density. And here is a tricky thing that is worth mentioning. Acoustic processes are so fast that the process is isotropic, so that there is no heat flow, and it's not isothermal. So if we use the ideal gas law and describe the change of pressure with respect to density, and as you see here with constant entropy, so isotropic, we got the result is the ratio of the pressure and the density by kappa, which is the ratio of specific heats. And this is what is normally equal to our squared sound velocity, as we will later see. In history, there was a first estimation of the sound speed, and this was created by assuming isothermal values. But if you do so, and you know this is 1.4, you got the wrong estimation of the sound speed. So this is very important to keep in mind. Why I'm presenting this, you might say, come on, if this is the practical value, why do you have this value here? I mean, this is a value that might occur, for instance, if the airflow is in fiber material. The fibers are cooling the air, keeping the temperature constant, and then you are more or less in this region. This is for free fluid. That's the value for free fluid. Okay, so as mentioned, now we have to linearize the equation because we have no steady flow in acoustics. So the changes in pressure and density are very, very small compared to the global density or the global pressure level. And now we introduce small changes. And the first step denoted by this prime here and by small p and also the small velocity also denoted by prime. If we enter this into the equation of continuity and neglecting all second order terms as far as the source terms, in addition we also assume that this is supposed to be zero, so there is no steady flow, and then we can linearize the equation of mass and momentum continuity, and we get this one. So the density is no longer in front of the Nabla operator, and also the velocity of the momentum equation simplifies a lot. We also know that all these linear equations are rotation free, so that means the rotation vector and can be expressed using a velocity potential. So we can use a potential to express the velocity, and that's a helpful quantity for many later derived wave propagation phenomena. The definition is given as such, so that's the velocity equals minus nabla, or the gradient of this velocity potential. Okay. In the following, we would like to get rid of this prime notation. So when we're writing when we write density, we are always talking about the small changes along the equilibrium. Good. So now let's derive the wave equation out of this. We perform the following operation. We take the left-hand side of the equation 58 and minus the time derivative minus the gradient of the right-hand side. Just to remember, the left-hand side was the mass continuity equation and the right-hand was the momentum continuity equation. And this is what we get. So much less complicated than the things before. We have squared time derivative and a squared gradient operation from the pressure. The target must be to get rid of this density expression, and this is when the equation of state comes into play. If we enter this, we get finally this equation, and this is the linear wave equation for acoustic pressure P. So we see the sound speed here relating those two terms. We have the second derivative with respect to time for the pressure, and we have the squared gradient, which could also be called a Laplace operator. Until now we have no source terms because we have neglected them in the first step. Now, if we enter our famous definition of the velocity potential into this, and into the linear equation of motion, so again the 79, we could also get the relationship between the pressure and the velocity potential. So they find was it for velocity, but we also need a quantity for the pressure. And if we do so, we get finally this equation that gives us the pressure. So it's the time derivative of this velocity potential multiplied by the static density of the fluid. So when we enter this into the wave equation and we eliminate one of the time derivatives, we get a kind of similar expression than the wave equation here upwards, but that's the wave equation for the velocity potential, looking quite similar to the expression 60. Good. We can apply this velocity potential definition and the equation 61 to derive the relationship between pressure and velocity. This is something that is very important to understand the properties of the sound field, and we just use the definition, enter the relationship for the pressure, and then we see that the velocity is the integral of the gradient of the pressure with respect to time. Good. We will later use that for harmonic waves. Harmonic waves. Let's start with the first solution of the wave equation. So in the first step we take one-dimensional wave equations, and there's a very practical solution which comes from D'Alembert, saying that every function of the form, which is any arbitrary function, but the argument is x minus speed of sound multiplied by t, and it could be minus or plus, is a solution of the one-dimensional wave equation. If we use as function f and g just simple harmonic functions, like this, and use the fact that omega divided by the speed of sound is the wave number, or we define it, that's given here, then we have two components of this one-dimensional harmonic solution. We have one A with a minus here, and we have one with a plus here. It's quite a simple thing. So this is a wave propagating in the positive direction, and this is a harmonic wave propagating in the negative direction. It's time to make some remarks of the symbols that we have here used here. I mean, you should be familiar with the symbol here on the left-hand side from the harmonic oscillator stuff. So we have the period, which is measured in seconds. We have the frequency of a harmonic oscillator, which is given in hertz. And for practical reason, writing some formulas much easier, as we did here, we use the angular frequency, which is just the frequency multiplied by 2 pi. As we are talking about waves here, now we have a space component on top of that. And we have similar symbols here. We have a spatial period, which is what we call the wavelength, and this is related to the time period via the sound speed. It's worth mentioning that there's nothing like a classical frequency in the space domain. So if we take the reciprocal of the wavelength, it's not practically used. That's a different thing. That means if we use some kind of angular space frequency, this is the wave number. So this exists, and the symbol normally used is k, and it's normally expressed as the angular frequency in time divided by the speed of sound. Just as presented here in the figure, you see that's a typical harmonic wave expressed in pressure. Obviously, the wavelength is when the pattern repeats, and if we take two different time steps, so the blue one is here at 0 seconds, and we just have half a second later, we see that the wave, which is given by orange, it's moving, it's propagating in space. Good. As mentioned, we have derived the relationship between the velocity and the pressure, and if we apply this to harmonic waves, the integration converts into the factor 1 divided by complex number and omega. So the relationship in harmonic waves is given by this expression here. If we apply this to one-dimensional waves and we take the wave in the x direction, we got this expression. So this is just applying the equation here on top, and then we get the same solution as the ansatz for the pressure, but divided by this quantity here, by the product of density and speed of sound. And that's a very important one, because actually this is the quantity that relates the pressure to the velocity. And in the pressure field or in the plane wave field, this is called the characteristic acoustic impedance. That's a quantity very important, because for any fluid or acoustic wave, it relates the velocity to the pressure. For instance, in air it's around 400, so that means pressure and velocity are not too far away. But if you take, for instance, water, it's 1.5 million, and this is a completely different relationship. So that means, for instance, this is why the pressure wave in fluid or in water with the similar pressure than in air is not that audible as a pressure wave in air. Okay, good. So in accordance with the impedance concept that we have already defined for mechanical systems, where we had force per velocity, we can do the same but using the pressure now in the sound field. And this is what we call the impedance. So not saying using the attribute a characteristic, it's just the acoustic impedance. Please note, if we don't have plane waves, if you have a specific pressure field, the impedance can become complex. That's something that's important, and it's describing in combination the fluid, but also the shape of the pressure field a little bit. Okay, so far for the one-dimensional thing, but introducing important quantities. When we switch to three-dimensional space, we use a wave number vector. So it's a similar expression, but we have a space vector multiplied by a wave number vector that describes our direction of propagation. We can also enter this into our harmonic, into the wave equation, and we get a similar expression. So the only difference is that we now have pressure function in 3 dimensions, but we also have the same expression with the omega divided by the sound speed, which is k in fact, and so on, and we have our exponential function and the j omega t term as we're using the positive convention. Similar to the harmonic oscillator, the term is very often omitted. We introduce the wave number, and if we rewrite this equation, we got the so-called homogeneous, because there's no source, but Helmholtz equation. So this is what is usually called the Helmholtz equation of acoustics. Good. So far for the wave equation. Now let's come to some field quantities. Field quantities that describes the field, and very important, that relates the sound wave or the fluid wave to energy quantities. This is something that we definitely need in energy methods as SEA. So the instantaneous power in the sound field is also defined as the force multiplied by the velocity. The force can be translated into the pressure and a balance area, which we call A. And this is a vector. We use a vector because an area also has an orientation. If we take the area as a scalar value, then we need a normal vector. That means the power flow in a specific area is given by pressure times area times the velocity and times a normal vector. When we use the acoustic intensity is defined as exactly this power flow but divided by the area, by the unit area, and this is then the pressure times velocity times a normal vector. So this is the so-called acoustic intensity. We can again use the time average, and we have the same effect then as we did for the power introduced, for instance, into a mechanical system, and the quantity that's an expression to calculate the averaged intensity or average over time gives the product of the pressure multiplied by the conjugate complex of the velocity, the real part of it divided by 2. When we use the harmonic wave solution and entering this into the equation 70, we have this as the harmonic solution for the pressure. The conjugate complex solution is given by this equation, and you know that the relationship between pressure and velocity given by the impedance. So this is why this density speed of sound term is here in the denominator. Then we get the following equation for the intensity, going through all the terms, having the doubling of the harmonic function, and then we get the cosine squared function here for harmonic waves. If we perform the integration, we finally get this relationship. So the intensity in a plane wave is the squared amplitude divided by the acoustic characteristic acoustic impedance and 2, or if we use directly the root mean square value, we get this expression. We just simply have to divide the squared root mean square value by the acoustic impedance. Or using the relationship between pressure and velocity, we can get a similar expression for using the velocity. So the speed of sound relates the energy density to this sound intensity. So you must imagine if you take the intensity and you divide it by the speed that this energy or this power is propagating, we get as the energy density. That's the squared pressure divided by a similar term, but now we have a squared speed of sound. So those quantities are very important in SEA because they relate the energy in a wave field. And as we, at the end of the day, in SEA just know the energy of our subsystem, we have to extract the pressure from this energy value. And this is exactly what we need there. The relationship between energy density, sound intensity, and the relevant field quantity, which is here in our case, the pressure. So, again, written down what I said in words before. What is also important is this energy, especially the intensity, are the quantities that relate the power that is irradiating the boundaries of the subsystem, and this is then very important for the estimation how the power and the wave fields are exchanged between neighbored or connected subsystems. When we have intensity quantities and would like to get the power flow in total back out of this, we just simply have to calculate over the surface. But, and please, that's very important, keep in mind, it's also the intensity is a vector quantity, and our balanced surface is also a vector quantity. So we also have to integrate over a real surface with the orientation in mind. Good. So, then the next point is in every wave field we have damping, and we had introduced some damping constants, and it's very important to link classical damping again to the damping loss factor in a wave phenomena. So we start with this equation where we have a constant complex amplitude, we have our wave equation solution for harmonic waves, and we have a damping term that damps the wave the longer it is propagating, and this is what we call the decay rate, similar to the decay rate for the harmonic oscillator, where time was the argument. Now it's space. There are several reasons for this attenuation of acoustic waves. It could be vicious damping, it could be thermal damping to irreversible heat flow in the wave propagation, it could be molecular damping, but it's not something that we just have to keep in mind, because we get those values from tests or from other assumptions. And our task here is now to link this alpha, to link the wave, let's say K, to our well-known damping loss factor. From the definition, we know that the damping loss is defined as the change of energy related to the total energy over one cycle divided by 2 pi. One cycle in time is also one cycle in space, so this is given by the wave number. And if we do so, we got this expression because we just take our amplitude in the beginning and then propagate just one wave number, entering this here into our equation, and then we got this expression. For relatively small alpha, and this is something that we can assume because at least we need some wave propagation, otherwise there would be no waves. We got this example, and if we write and summing up all this together, we get the following relationship using this relationship between lambda and k, and then we see that the decay constant is given by the damping loss factor and k divided by 2, or in other words, damping loss factor is 2 alpha divided by k. Similar to the, let's say, there's a spring constants other, it's a good habit to introduce a complex wave number. That means to introduce this quantity here directly into the wave number, so that we don't need an extra term, because the complex wave number can at the same time describe propagation and the damping in one constant. And if we do so, we see that we're just rewriting the solution for alpha that we have received. And then if we compare this with the classical definition, if we create this complex alpha, or if we compare this k with the, let's say, all the terms that we have here on the right hand side, we have to write k like this. So it's a k as it is, and minus j eta divided by 2. So that means if we know the damping loss factor of a fluid system, we can represent the harmonic waves by this expression of the damping. So please, in this context, but please keep in mind, this does something with the speed of sound. It's slower then. So the speed of sound changes because the denominator is getting bigger or smaller, whatever. And the same is true for the impedance. So this changes the typical field quantities or the important quantities of acoustic waves. Good. Finally, the symbols for velocity, acoustic impedance, intensity, energy density, and acoustic power are summarized here in this table. The important formulas that relate the different quantities, the units that are used, and typical and important, let's say, formulas for plane waves. So what are the relationship between pressure, what is the impedance, what is the intensity of a plane wave, what is the energy density of a plane wave, and what is the power in irradiating a specific area of a plane wave when it's hitting it in normal, and the link to the equations. Good. So that was session 6. In the next session, I will talk about fundamental acoustic sources. Again, an important thing, especially for statistical energy analysis, because sources, they are the means to introduce energy or to introduce sound fields in general into fluid field. And if you understand the sources, you have the first step done to describe how energy system or how SEA subsystems are linked together. have fun. I hope you enjoyed this session, and looking forward to seeing you for session number 7.